Hi, I'm going to give a perspective on the recent reports claiming room temperature superconductivity in thin films of gold and silver nanoparticles. So the original paper was posted on the archive 10 months ago, and they were looking at these agglomerates of gold and silver uh, nanoparticles and measuring electrical and other properties. And the most striking signature that they claimed is related to superconductivity is a resistance of these films as a function of temperature, showing a very sharp drop, which would appears to go to zero below critical temperature. And this temperature depends on the sample, and in particular, they report one device that has a transition above room temperature. So this is a very striking result, and if it were reproduced and really true, it would completely transform all of electronics, and it would have a just an enormous impact globally. So the when the paper came, the manuscript was posted on the archive. It was pointed out by Brian Skinner that there were some peculiarities in the the noise signature down here. That basically, if you look at these different curves taken at different magnetic fields, that they seem to be displaced by a constant value, but the random features here um, seem to be repeating, and this was um, superficially similar to Hendrik Schoen's repeated noise that led to his downfall. Nobody is saying that that's what's happening. That's what happened here. But we looked at this. My colleague David Pecker and I, we were intrigued by the manuscript, and we're trying to understand if there were any uh, alternate explanations of the resistive transition, which is the one that, of course, if you have zero resistance, that would be, we can make power lines and, have, electronics that basically doesn't dissipate energy. So basically what we surmised is that because this is a sort of a network of nanoparticles, that they're basically touching one another, and if for some reason there is a sort of a relative expansion, say, of the substrate, they could start to move apart from one another, and that could be driven by temperature. And if that happens, then basically there's a sort of well-known percolation transition where the conducting islands basically break up, and they become smaller than the system size below, in this case, below some critical temperature. So what we were thinking was that if that was indeed happening, you could still drive current through the system if you applied a large enough current, or you basically source enough voltage. So you could imagine having, let's say, three of these percolating areas, non-percolating areas, basically to have like tunneling between the necks that separate them. But if the voltage leads were not connected to the current path, then they would basically float to whatever value, or these two might be even connected to each other, but not to the current leads, and you would measure zero voltage. So the way that these four terminal measurements work is you measure the current that is flowing through the device, that's delta I, and then you measure the voltage that that goes across the separate leads, and you want to do that because you don't want to have a contact resistance. So this is a very standard technique, but it's really important that the sample, that the leads themselves be electrically connected to the sample in order to really be measuring the resistance. So we suggested that IV curves be shown or measured, and that if you looked carefully at these IV curves, you would be able to tell, for example, that all of the leads are connected and everything is ohmic before it goes superconducting or even after it goes superconducting, to make sure that you're really measuring what you think you're measuring. So we had some constructive suggestions. So 10 months later, there's an updated report on the arXiv, many more scientists involved, and they have changed their title a little bit, and they're focusing on what they observe. So there's this coexistence of diamagnetism and vanishingly small electrical resistance. So that's certainly an improvement. And they do go into great detail about the technique that they use. They show exactly, so they have now a new setup that they use 8 pins, and they're going to do multi-terminal measurements, and that's a very reasonable thing to do. In particular, what they do is basically put the film down on this system that has 8 contacts, and then they can measure currents and voltages between any of the 8 contacts. And they also report the voltage sensitivity for which they can measure when they measure the voltage. This is the sensitivity. It's in the order of 25 nanovolts. So they're able to resolve very small voltages, which is a good thing. And they still, report these resistive transitions. So here you see at the higher temperature, 274 Kelvin, you see this IV curve here, and then at 260 Kelvin, you see that it's basically flat, so there is no voltage. And so this is what you would expect if you had a vanishingly small resistance. Notably, there is no update to the susceptibility measurements, and this was also pointed out by Brian Skinner. And so they do acknowledge that there is a repeating noise, and they think that it might be real, but they don't say too much about it. And they have not performed updated measurements of the susceptibility. So again, I want to focus on the transport, electrical transport, basically, where they're measuring voltages and supplying current. In particular, in the very long supplementary document to the manuscript, they do show some 2-terminal IV curves, and these are the 2-terminal IV curves. So they show them at higher temperatures where they're purportedly in the normal state, and then they show them at 170 Kelvin where it's presumably in the superconducting state. They don't say which sample this is, or they don't show the IV curves in the 4-terminal IV curves in the superconducting state, but not doubting that part. If you look at these curves, though, and you look at them closely, what you'll see is that there are a number of abrupt transitions, in particular in the transitions for leads that are from one side of the sample to the other side. So this kind of thing here that you see, this jump here, the fact that there is hysteresis at all is a very alarming thing, right? This is not linear behavior as they describe, or ohmic behavior as they describe in their manuscript. And also what we don't see are the close-up here. So remember, they can measure nanovolts, and what they're showing here is volts, basically. So they're really not probing in a regime where you might expect to see basically floating leads, voltage leads that could lead to the measurement of zero resistance. So in addition, they also show a lot of other things which I think are somewhat troubling. But they do show the data that they see this reentrant transition. So as you lower the temperature, it goes to 0, and then it goes back to the previous value, then it goes to 0 again, then goes back, and then goes. So this itself is probably unprecedented for any superconductor, that you would have this multiple reentrant transition. However, if there are if there are change, it's definitely something that could be that would be consistent with having percolating and basically movement of these nanoparticles as a function of temperature that could lead to connection and disconnection of the voltage leads. So that's basically where things are at the moment. Not at all convinced that they are measuring a zero resistance state. And I think that there are clearly follow-up measurements that could be done, higher resolution measurements, more sensitive measurements of the voltage, the transport, the IV characteristics at low voltage between the voltage leads and the current leads when the sample is in this vanishingly small resistive state. So until those measurements are performed and shared with the community, I think that there should be some skepticism about the claims of having vanishingly small resistance. But the last thing I want to say is that this is normal science. This is how science should be done. I don't believe this paper should be accepted in a journal at the moment. And I think that there is more work that could be done with probably very little extra work on the part of this team. And it's a very exciting, prospect of having superconductivity, and I think everybody would like to have that. So I'm hoping that these follow-up measurements will be reported in an updated version of the manuscript.